Hello, my name is Stephanie Pena, and today I will be discussing fluorescence microscopy. This is the table of contents. Today we will be discussing fluorescence microscopy, the intro, principles, the applications in quantum mechanics, technique and methods, research articles, and some fun facts. What is fluorescence microscopy? Fluorescence microscopy is defined as an optical microscope that uses fluorescent or phosphorescent instead of or in addition to reflection absorption to study properties of organic or inorganic properties. Fluorescence is created when a substance absorbs light and emits a colored light. The light source is mercury arc lamp and tungsten or halogen lamp. Scientists use fluorescence microscopy to detect proteins and molecules in tissue cells. Fluorescence differs from other microscopes because it has higher intensity than other microscopes. As you can see on your top right corner, there is a mercury or xenon arc lamp, which has the highest intensity than the tungsten halogen and the LEDs. Here are some pros and cons from using the light source. And then also the fluorescence microscopy provides information of photons. So how does it work? The function of fluorescence microscopy begins with the light source. The mercury light source are most commonly found in labs, but there is also the tungsten halogen lamp or the xenon arc lamp. We also have a diphoric mirror, which reflects light to pass and permits wavelengths to pass through. And then with that comes the excited filter and the barrier filter. The excited filter has specific wavelengths that pass through the barrier filter, and then which then passes to the specimen. The barrier filter blocks wavelengths and allows specific wavelengths to pass. And then this then goes on to the detector. As you can see on your top right corner, you can see the laser as it shines to the diphoric mirror and then moves up to the objective and the sample. But underneath that, we have the filter, which blocks, and then from the bottom of that, you can see another light source.
Principles of fluorescence. Fluorescence unfolds in a series of absorbing, exciting, and emitting light. When certain materials encounter light, they absorb photons at precise wavelengths, causing electrons to enter a state of temporary excitement, rising to higher energy levels. As these excited electrons return to their lower energy states, something remarkable happens. Excess energy is released as photons of longer wavelengths, resulting in the characteristic fluorescent glow we've all witnessed. This shift in wavelength, known as soak shift, distinguishes emitted light, persisting briefly even after the initial excitation. The applications of fluorescence spans diverse domains, from microscopic labeling to advancements in material science. Application in quantum mechanics. Quantum principles serve as our guide in understanding how substances emit light when stimulated by photons, particularly in the context of fluorescence. This discrete energy levels of electrons within atoms and molecules as described by quantum mechanics. As previously mentioned in the last slide, molecules absorb energy, electrons leap to higher energy levels. This occurs as electrons return to their lower levels, emitting distinct photons in the process. This image on the right describes the fluorescence features of two different creatures, the bird and the crustacean. For the bird, it illustrates photos taken under white light of UV fluorescent excitation, showcasing fluorescent cheek and crown feathers. There's also an analysis of the reflectance and spectral sensitivities. The crustacean is depicted in frontal aggressive display under white light and blue light excited fluorescence, along with the images of the crustacean in its habitat under fluorescent excitation. Additionally, this image discusses the spectral sensitivities of the crustacean photoreceptors and their match to fluorescent emission. This primarily focuses on visual observations and spectral analysis of fluorescence in these creatures under different light conditions and their natural environments. And this other image on the right is called the quantum yield. The quantum yield is a ratio of the number of emitted to the number of absorbed photons.
So there is a difference between atomic and organic molecular fluorescence. In this equation, Planck's radiation law is practiced, as n is the energy level, where n is the principal quantum number, as naught is the ground state of the atom. The ground state cannot have angular momentum and is known as a singlet state. H is the Planck's constant. This is the frequency, this is the speed of light, and this is wavelength. When n is greater than 0, there are parallel states that consist of angular momentum. If there are 3 possible directions of angular momentum, the degeneracy is known as a triplet state. And for the atoms to transition between various energy levels, the atom must emit a precise wavelength. This is an equation of a system going to a first excited state, and it shows that fluorescence intensity is proportional to the total concentration of fluorophore. And once in the excited state, the molecules will stay there for a while and then decay back to the ground state by emitting light of identical wavelengths, and the transition between single states and triple states violates the conservation of angular momentum. On the other hand, organic molecules do have a fast fluorescence with a steady state lifetime, and the energy levels become bands because the molecules can have large number of vibrational states and intersystem crossing. Moving on, fluorescence is sensitive to molecular environmental changes that affects quantum efficiency and spectra of fluorophore, and a problem that research encounter is fluorescence photobleaching, but scientists have also found a technique known as fluorescence recovery after photobleaching. And lastly, this is a tool used in biology and biochemistry research, and there are 4 methods to measure fluorescence in the time domain. On the next slide, we will talk about the advantages and disadvantages of fluorescence microscopy.
So some advantages for fluorescence microscopy is that it has a lifetime of 300 hours, it has higher specificity, it gives a clear 3-dimensional internal structure, it has interchangeable probes, it is relatively cheap, and is widely available in labs. Some disadvantages of fluorescence microscopy is that it has a long warm-up time, it has a short lifespan, and at times gives false information when interpreting the image it gives. There's also staining, bleaching, and it has low penetration. A research article by John Daniel titled Advanced Fluorescence Microscopy Techniques for the Life Sciences mentions that fluorescence microscopy has a very important role in making decisions in biomedical research, and that it has been drastically impactful in the life sciences for analyzing molecular structures. It has allowed for analyzation of cells in the single molecular level, and in quantum mechanical treatments for an atom shows that the probability of an associated electron possessing an amount of available energy of occupying any energy level of the atom. To wrap things up, some fun facts about fluorescence is that if you sprinkle salt crystals onto a candle flame, the sodium atoms excite with the heat and produces a bright yellow light. On the slide, you can also see an image of onion cells underneath a fluorescence microscope. And that brings the lesson to a close, and thank you for listening.